Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Capacitance-voltage characteristics from the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the capacitance voltage characteristics of metal oxide semiconductor devices are discussed. Also, low frequency capacitance voltage profile of metal oxide semiconductor, that is MOS structure, is studied and different regions obtained by sweeping the gate voltages are explained. In this module, the quantitative expression of high frequency capacitance is obtained as a function of surface potential. Also, charge distribution in N-type MOS is explained in different regions. Now, coming on to CV profiling. CV profiling is also known as capacitance voltage measurement technique, and it is employed for characterization of semiconductor-based resources as well as devices and for the physical parameters extraction. Fundamental principle underlying the capacitance voltage measurement involves applying a variable voltage to a metal insulator semiconductor, also known as MIS, or to a Schottky junction, and then measuring the junction capacitance. In order to derive the relative information of DUTs, that is, device under test, physical properties, the correlation between the measured capacitance and the applied voltage is utilized. A capacitance voltage testing setup has numerous significant merits that make it a precious platform and an essential device in the field of ICs, that is integrated circuit industry, and it currently has a great use in the field of photovoltaics. It is the most efficient electrical measurement system in order to collect materials and devices information. Moreover, it is very easy to handle, fast performing. Also, it can be easily adjusted for use in various kinds of investigations. In comparison to different characterization techniques, this analysis system is quite cheap. Through this measurement system, multiple analyses can be performed like profile of doping, average doping concentration, as well as lifetime of carriers. Capacitance voltage measurement result can tell about the thickness of oxide, the charges of oxide, and contamination from mobile ions, and interfacial trap density in wafer processing. These measurements are usually carried out after every important fabrication step, such as gate dielectric and polysilicon deposition, metallization, etc. Eventually, results give information of how the device is affected by the various processing parameters and chemicals. CV measurement is again utilized in testing of finished devices in order to determine other parameters such as threshold voltage or to model final product performance. Let us now discuss the capacitance voltage profile curves. In metal oxide semiconductor device, two capacitances are considered. One is the static capacitance and other is the differential capacitance. Static capacitance can be defined by the equation C stat is equal to Qt divided by Vg. Here, Qt denotes the capacitor plate's total charge density and Vg denotes the voltage biasing which is applied to the capacitor. Differential capacitance is more significant, which is defined by the equation C equals to dQt by dVg, and it determines the rate of change of the total charge density with respect to voltage. In this discussion, the term capacitance will be referred to as small signal metal oxide semiconductor differential capacitance. Some related formulas and the theory-based derivations will be shown further on in the presentation. Ideally, when there are no interface traps, oxide charge of work function difference in metal insulator semiconductor structure, total capacitance per unit area is equivalent to the series combination of the oxide capacitance and silicon capacitance as 1 by C equals 1 by Cs, that is Cs a function of psi s plus 1 by C ox. By applying low alternating voltage, that is a sinusoidal wave in a steady state system, measurement of capacitance can be done as a function of gate biasing. Small signal range is selected in order to conduct the measurement. What it means that exerted AC voltage amplitude is sufficiently less to achieve linear response of AC current to AC voltage. Some non-ideal effects such as interface traps and oxide charges have an impact on the small signal range as they influence the velocity of admittance change of metal oxide semiconductor capacitor with gate bias. We will next study the capacitance voltage profile at low frequency. In MOS structure, low frequency, that is LF, differential capacitance per unit area as a surface potential function can be obtained when minor charge carriers are capable enough to follow the AC gate voltage and bias voltage ramp for each bias voltage value. For deriving the analytical formula for LF capacitance voltage, consider the device to be thermally equilibrated as well as the concentration of dopant impurity to be uniform in silicon. Thus, one-dimensional space potential as well as electric field can be obtained by solving Poisson's equation, whereas Gauss law is used to compute surface charge per unit area at the interface. The electric field is given by F of S is equal to sine of UB minus US into kT by Q times lambda I into F of US UB, where F of US UB is equal to, within the brackets, square root of 2 times within the brackets UB minus US into sine hyperbolic of UB minus, within the brackets, cos UB minus cos hyperbolic US, both the brackets closed. FUSUP is the electric field with no dimensions. Lambda I is equal to Debye's length for intrinsic silicon. UB is equal to the bulk potential and US is the surface potential. Bulk and surface potential are defined as UB is equal to EF minus EI divided by Q. US is equal to EF minus EI at the surface divided by Q. Surface charge density can be evaluated using Gauss law as follows. Qs is equal to kT by Q into epsilon s by lambda I sine of UB minus US into F of US UB. The differential capacitance of surface is defined as Cs is equal to minus Q by kT into delta of Qs by delta of US. Now derivating the above equation for Qs with respect to US and substituting in the expression for differential capacitance of surface, we will obtain the final formula for Cs, that is differential capacitance of surface at low frequencies, as Cs is equal to minus of sine of UB minus US into epsilon s by lambda I into sine hyperbolic of US minus sine hyperbolic of UB divided by F of US UB. Theoretical low frequency CV curve is represented in the figure. By sweeping the gate voltage, different regions of CV curve can be obtained. Considering a p-type silicon wafer, the first region is said to be accumulation region. This is obtained for negative gate bias. When negative gate biasing becomes very large, hole charge density at the surface of silicon gives rise to a large differential capacitance Cs, such that the total differential capacitance of the MOS structure is roughly equivalent to the oxide capacitance per unit area, that is Cox. On the other hand, for less negative gate bias voltages, the hole charge density at the silicon surface decreases, which leads to smaller value of Cs. Flat bend point is a point at which gate biasing eventually becomes equivalent to zero. When small positive value of gate voltage is applied, then holes get repelled from the surface of silicon, leading to the formation of a depletion region of ionized dopants. The depletion region is also termed as depletion layer. The depletion layer becomes wide when more positive biasing is applied, thereby making Cs smaller. Therefore, we have stated that the total capacitance of the MIS structure decreases. With increasing gauge biasing, the hole density of the surface declines, whereas the electron density rises. The point when these densities attain the same value is known as inversion onset. Once the surface density of electron exceeds the surface density of holes, electron inversion layer is produced. When the gate bias becomes more positive, differential capacitance Cs increases continuously till it becomes comparable and then subsequently exceeds the oxide capacitance per unit area, that is COX. Therefore, we can say total capacitance C of the metal insulator semiconductor structure approaches COX asymptotically. Let us now calculate the capacitance voltage profile at high frequency. This section presents the quantitative expression of the high frequency capacitance as a function of surface potential. When the frequency is high, then minor charge carriers do not follow AC gate voltage. Instead, they follow the changes in gate bias. Main difference in low frequency and high frequency capacitance voltage curve can be noticed in the inversion regions, that is, weak and strong. Once the major and minor charge carrier concentrations are equal, a hypothesis is formulated such that the application of gate bias in equilibrium condition keeps the total amount of minority charge carriers fixed, and this does not change even on applying AC voltage. Additionally, spatial rearrangement of inversion layer is considered, that is, widening and narrowing of the inversion layer happens in response to the AC gate voltage. Computation of high-frequency capacitance can be carried out in a manner similar to the one utilized for the low-frequency case. That is, Cs is equal to 2 times CFBS into within the brackets 1 minus e raised to power minus VSO plus small ni by Na whole square plus within the brackets EVSO minus 1 into delta by 1 plus delta plus 1 brackets close into F inverse of VSO mu B, where delta is equal to F of VSO UB divided by e raised to power VSO into within the brackets the integral going from 0 to VSO e raised to power Vs minus e raised to power minus Vs minus 2 times Vs divided by F cube of Vs UB into dV minus 1. Even though the equation as mentioned in the previous slide can be used to obtain accurate results, linear approximation can be carried out while considering minority charge redistribution. The results obtained with this approximation only deviate by approximately 1.5% from the actual value of capacitance. This approximation considers the capacitance from as calculated in the previous slide to be independent of the gate bias after a certain value of band bending, which is denoted as Vm, which is also termed as the match point. The approximation error is greatly reduced at the match point due to the capacitance at this point. The approximate values of capacitance for p-type and n-type are computed using the following formulas respectively. Cs is equal to 1 by square root of 2 into CFBS into within the brackets 1 minus e raised to power VSO into, within the brackets, VSO minus 1 plus e raised to power minus VSO, brackets close, raised to power minus 1 by 2. CS can be simplified to be 1 by square root of 2 CFBS into, within the brackets, e raised to power VSO minus 1 into, within the brackets, minus of VSO minus 1 plus e raised to power VSO, brackets close, raised to power minus 1 by 2. A suitable approximation for the band bending match point is Vm is equal to 2.10 UB plus 1.33. High frequency capacitance voltage profile curves are fundamental for MOS structure measurements. The use of high frequency and low frequency capacitance techniques, CV profiling, can be used to determine the interfacial trap density as well as other physical parameters. However, the high frequency capacitance voltage profile curve that is acquired experimentally is the only good approximation of the device true CV curve throughout the biasing range. After approaching flat band region, the majority charge carrier density decreases sensibly, yielding the more rapid capture in addition to shorter trap constants at the interface. For the employed measurement frequencies, interface traps follow the AC gate voltage over a certain range of gate bias, thus restricting the bandgap energies over which the interface trap level density can be extracted via high frequency CV profiling technique. The deviation of 1 MHz CV curve from ideal high frequency plot can be attributed to the strong capacitive response of interfacial traps as flat band regime is reached, resulting in small values of the apparent interface trap density being estimated. Thus, as flat band regime is approached, measured 1 MHz capacitance rapidly follows Cox in comparison to the actual high frequency capacitance. The fast variations in capacitance with gate bias impacts the slope and diminishes the stretch out and resulting in lower estimations of interface trap level density via any procedure involving high frequency CV profiling. The deviations at 1 MHz have been found to be below 2% in the region from flat band to strong accumulation. We will next study the CV characteristics of metal oxide semiconductor, that is MOS structure. The MOS capacitor comprises a metal oxide semiconductor structure which is shown in the figure. It shows a semiconductor substrate which is having a thin oxide layer and metal contacts which is described as the gate. Second metallic layer is to create the ohmic contact to the semiconductor bag which is known as the bulk contact. The structure with p-type substrate is termed as n-type MOS or NMOS capacitor since the inversion layer contains electrons. To appreciate the various biasing modes of a MOS capacitor, let us consider three bias voltages: A. Less than flat band voltage VFB, B. Greater than flat band and smaller than threshold voltage VT, and C. Larger than VT with the bias regions termed as accumulation, depletion and inversion operation mode respectively. All these modes and the charge distributions are provided in figure 3. As can be seen in the figure, accumulation takes place for negative voltages and the negatively biased gate draws holes from the substrate towards oxide semiconductor interface. Depletion takes place in positive bias voltages. Positively biased gate repels holes into the substrate, thus depleting the interface of mobile charge carriers, and a negative charge due to ionized acceptor ions develops in the space charge region. The flat band voltage VFB is defined as the voltage which is separating accumulation and depletion regions. Inversion takes place for voltages larger than threshold voltage. In inversion regime, a layer of negative charge develops at oxide semiconductor interface besides a depletion layer. Inversion layer develops because of the minority carriers drawn towards the interface by a positively biased gate. Figure 4 shows the energy band structure of NMOS capacitor which is operating in inversion regime. The oxide has been shown as a semiconductor having a large band gap. Therefore, it obstructs the carrier flow between the gate and the semiconductor. Band bending occurs in consistency with the incidence of the depletion layer. At semiconductor oxide interface, Fermi level lies near the conduction band, indicating the high density of electrons. Thus, we have studied that there are different operation modes of an MOS structure: flat band, depletion, inversion, and accumulation. Flat band is the condition of no charge in semiconductor and a flat energy band. Surface depletion takes place when holes are repelled by the positively biased gate. A higher positive bias draws electrons, which are minority carriers, to the surface and forms inversion layer. With negative bias, the gate draws holes from substrate towards surface, causing accumulation. Let us next discuss about the flat band diagram. Flat band signifies flat energy band structure in semiconductors, implying that no charge is present within the semiconductor. The flat band for aluminum silicon dioxide, silicon, that is AlSiO2Si, MOS, is given in figure 5. The voltage VFB needs to be applied to get the flat band diagram. Work function of gate Fn, electron affinity of oxide C oxide, and silicon and the band gap of silicon Eg are also indicated in the figure. The flat band voltage is obtained when the applied gate voltage matches the difference in work functions of gate and the semiconductor. By applying low voltage to a metal, its valence band edge may be shifted away from Fermi level, and holes they are pushed away by the gate, decreasing the carrier density and lowering the capacitance, which can be seen as the valley in the middle of figure. Coming on to inversion, at large gate bias, the conduction band approaches Fermi energy level, filling the surface by electrons in inversion layer or N-channel at semiconductor oxide boundary. This causes increase in the capacitance, which can be seen in the figure. Let's now understand accumulation. The negative gate source bias forms a p-channel at the surface of N region, which is similar to the case of N-channel, although it is having opposite charge and voltage polarities. The increased hole density results in increased capacitance, which is observed in figure. So students, Let us now summarize what we have learned in this module. In this module, the capacitance voltage characteristics of metal oxide semiconductor devices were discussed. Also, low frequency CV profile of MOS structure was studied and different regions obtained by sweeping the gate voltages were explained. The quantitative expression of high frequency capacitance was obtained as a function of surface potential. Also, charge distribution in N-type MOS was explained in different regions. Thank you, students, for your attention.